Welcome to Real Analysis 1. This presentation is just some background material that you're going to need from your senior level analysis course that's going to play a big role in this graduate Real Analysis 1. What we're about to look at is a hodgepodge of definitions and results and theorems. This particular presentation contains no proofs. This is background you should have. This is more just to jar your memory and get you up and running when we start talking about least upper bounds and greatest lower bounds and Cauchy sequences and all that good analysis stuff that'll be necessary for this graduate course. So statements of definitions, theorems, a handful of examples from Analysis 1, our math, 4217 or 5217, cross-listed senior level graduate course. The two texts I've depended on are texts used in the Analysis 1 class are Kirkwood's Introduction to Analysis. I taught that Analysis 1 class throughout most of the 90s and into the 2000s. And the book I used was this Kirkwood book. It's a thin book. It's an excellent book. It's got all the basic stuff in it. Some of my colleagues throughout the 2010s and on into the 2020s, I think, are using Kenneth Ross's Elementary Analysis, Theory of Calculus. It's in a second edition. There's a newer edition out since 1980. And the book that we'll refer to most often throughout the course is Halsey-Royden and Patrick Fitzpatrick's Real Analysis. Fourth edition, 2010. There's a revised printing out that's fixed a few of the typos in the 2010 edition. I'll supplement the class with some other things, not too much. We'll stick pretty close to Royden. I shall refer to this book simply as Royden throughout the class. Excellent book. I know my way around some of the analysis books, and I think Royden and Fitzpatrick, this is the best. And the fourth edition is even better than the earlier editions. I took my graduate level real analysis sequence out of, it was the second edition of Royden. Fitzpatrick comes in as a co-author on this fourth edition, by the way. Okay, so for some material, it's kind of assumed, you know, you're up to date with your math, reasoning, proof techniques, induction, set theory arguments, logic like contrapositive and things like that. Our first result, I will state numbers in here as give these definitions and theorems numbers, and in the material in this graduate level class, I'll refer to these by the numbers in this background material. So theorem 0.1, De Morgan's laws. I'll also often quote the result from Kirkwood and the result from Ross, and if it's in Royden, Royden has a preliminary chapter, then the result from Royden. De Morgan's laws say, if we have a collection of sets, A sub I, indexed by indexing set capital I, then the intersection of all those A sub I's, complement of, using a little superscript to indicate complement, the complement of the intersection is the union of the complements, and the complement of the union is the intersection of the complements. So, standard argument, proof of which would follow just by the definition of union, intersection, and complement. One of my favorite questions, again, in these upper level classes is, hey, how many A sub I's are there? Is it a finite number? Is it a countable number? Is it something else? How many are there of these A sub I's? Well, there's one for every index I in the indexing set capital I. So I can't give you anything kind of a smart ass answer. There's a cardinality of capital I of them. However many indices, that's how many sets there are. With the emphasis going on the fact that this need not be a finite collection of sets. It need not be a countable collection of sets even. We'll talk about cardinalities around the end of this blast of material that we're going through now. But arbitrary intersections and arbitrary unions is what De Morgan's laws deal with. All right, you need to know, what the real numbers are in this real analysis class. The following is contained in each of these background references, and we'll define the real numbers with three kinds of axioms: field axioms, an axiom of order, and an axiom of completeness. The field axioms, usual idea of a field from an algebra class. A field F is a non-empty set together with two operations denoted as given here, called addition and multiplication respectively. So we're indicating multiplication occasionally with a little dot, addition with a plus sign, of course. And we require axiomatizing what a field is, if you like. We require the following to hold. Take two elements of the field, then the sum of those elements and the product of those elements are uniquely determined elements of the field itself. In other words, the algebra folks would say it like this: addition and multiplication are binary operations. Take any three elements from the field, then we have A plus B, parentheses, plus C equals A plus, parentheses, B plus C, associativity of addition, and similarly with multiplication, associativity of multiplication. So the two binary operations are multiplicative. We, in a field, have commutativity of both binary operations. A plus B equals B plus A times B equals B times A. Commutativity of both binary operations. Is there a group here somewhere? Not yet, because we hadn't talked about inverses or identities. But we could restate the definition of a field in terms of groups, in part at least. We need the two binary operations to interact. And we do so by saying multiplication distributes over addition. For any three elements of the field A, B, and C, A times B plus C equals A times B plus A times C, distribution. Axiom 5, there exists 0 and 1 in the field. Distinct 0 and 1 are different. The smallest field has two things in it, 0 and 1. And these, this thing here, this symbol, satisfies the property that symbol plus A equals A. This symbol here, the 1, satisfies 1 times A equals A. And this holds throughout the field. So 0 is the an additive identity, and 1 is an multiplicative identity. I'm sure these are probably unique, and that's one of the first things you show in a senior level analysis class, is that the additive identity and the multiplicative identity are unique. We'll call these additive identity and multiplicative identity downstairs. In a bit more of an abstract setting, we'd simply refer to this as the additive identity. Of course, we're dealing ultimately with real numbers. That's what we're trying to define. So I'll use the word 0 for that and 1 for that. If we take an element of the field A, then there exists a additive inverse of that element. That is an element such that A plus the additive inverse equals the additive identity. And if we take an element of the field that's not 0, that is not the additive identity, then there exists an A inverse such that a multiplicative inverse, A times A inverse equals 1. So no division by 0 in a field, no division by 0 in math, it's meaningless. But a lot of commutativity. You've got experience with algebra, then you know commutativity is not something you always have. In a field, you've got commutativity of both binary operations. You've got identities and you've got inverses. A weaker algebraic structure might be a ring. In a ring, you might not have commutativity. You might not have the inverses and the identities. You could have a commutative ring. We could have rings that have identities. But we're interested in really the most structure. We're interested in a field. Some examples of fields are Z sub p, integers mod p, where p is prime. That's not the only examples of finite fields, but these form finite fields. Do the arithmetic the usual way, reducing modulo p, in other words. The rational numbers form a field. The algebraic numbers, form a field. The rational numbers extended algebraically, extension fields. Rational numbers extended by the square root of 2 and the square root of 3, say. These form a field as well. The real numbers form a field. I mean, that's what we're working on defining. The complex numbers form a field. So there's some examples of fields. Here we've got finite field, z sub p, where p is an integer. All these other examples are infinite fields. The fact that I can't say the field says, well, if I'm going to define something here, the real numbers, I need more axioms. So we haven't tied it down to a unique mathematical structure just yet. So we're going to require that the reals be ordered in the following sense. For field F, F is an ordered field if it satisfies the following. There is a subset P of field elements called the positive subset, such that if A and B, let me just read this as are positive, because that's ultimately what we're getting to. If A and B are positive, then their sum is positive. If A and B are positive, then their product is positive. And if we choose anything in the field, then exactly one of the following holds. A is positive, the additive inverse of A is positive, or A equals 0. The law of trichotomy, this last thing is called. So in other words, part 1 and 2 tell you that set P is closed under addition and closed under multiplication. And there's 3 kinds of field elements in an ordered field. There are the positive elements, the elements of P, the elements whose additive inverse is positive, might want to call those negative elements of the field, and then there's the additive identity, there's 0, which is neither positive nor negative. Law of trichotomy. Now, when you hear ordered, you might be thinking more along the lines of greater than and less than. Well, we can use this to define a greater than less than. We would do so as saying, if we have a field with a positive subset P, we'll say A is less than B if B minus A is in P, if B minus A is positive. Or if you like, B is greater than A. So there's how the greater than, less than thing is related to this idea of a positive subset. And that's why it's called an ordered field, because it allows us to put this type of ordering on it. Those examples of fields we looked at above, integers mod P, not ordered. There's not a positive subset for those. The rationals are an ordered field with the usual kind of greater than, less than that you're used to. The rationals algebraically extended by a couple of algebraic numbers, ordered. The reals are ordered. All of these are ordered under the usual greater than, less than. Funny story, the complex numbers are not ordered. Click on the link in the notes, the online notes, so hyperlinked to some notes from Complex Analysis 1. In which it's shown that the complex numbers are not ordered. In other words, the complex numbers do not have a positive subset. You can't classify every complex number as positive, negative, or 0. It won't work. The imaginary numbers cause some problems. So not ordered here. The complex numbers are not ordered. So we still got multiple structures that form ordered fields. I didn't mention this one, but the algebraic numbers also form an ordered field. So we've got more than one ordered field, so we can't use these ideas alone as a definition for a single mathematical structure, the real numbers. A little side definition on our way. An interval in an ordered field is a set A containing at least 2 elements such that if R and S are in set A and R is less than S, and if T is an element in the field such that R is less than T is less than S, this makes sense because we're in an ordered field, then T is an element of A. That's just a symbolic way of saying the same thing you're saying in a calculus class. I've got an interval if it's a set that contains more than two numbers, and for any two numbers in the set, everything in between them is in the set. And that's what this is saying. Any two numbers R and S, if T is between them, then it's also in that set. That's what an interval is. We could classify intervals in terms of whether they have endpoints or whether they contain their endpoints. We could have closed and bounded intervals. We could have open and bounded intervals. We could have closed unbounded intervals. We could have open unbounded intervals. We could have half open, half closed intervals. See calculus notes for that. I warned you this was just a shotgun blast of definitions and properties. I don't even have any pictures in this, but there's pictures in my notes, say for the senior level analysis class. So we'll mention the intervals now because it's related to the ordering. So I can speak of intervals in any ordered field. But back to our definition of the real numbers. The real numbers form a continuum. And we need some way to say that. The rational numbers, they don't form a continuum. There's holes in the rational numbers. There's holes in the algebraic numbers. They don't include the transcendental numbers, for example. There's holes in the rational numbers algebraically extended by the square root of 2 and the square root of 3. They don't include the square root of 5, for example. So we need this concept of continuum somehow or other. And this concept of continuum is what makes all the limit stuff work. Without limit stuff, you ain't even got calculus. And all analysis is sort of rigorous calculus in a sense. So in order to axiomatically define the real numbers, we need to address the concept of completeness. And it's completeness that gives us the idea of a continuum. So this concept of completeness will ensure the real numbers are a continuum, that the real numbers don't have any gaps or any holes in them, like the rational numbers. The rational numbers are just shot full of holes. So the rational numbers will be an example of something that's not complete. We need a little definition first. Let A be a subset of an ordered field. So this is being done in rather a general setting. If there exists B in the field such that A is less than or equal to B for all lowercase a in set A, then B is an upper bound of set A, and set A is said to be bounded above by B. And all we said was everything in set A is less than or equal to this field element B. So B is an upper bound for set A. So the words are very suggestive. And similarly, we can define lower bounds. If there's a C in the field such that we have C is less than or equal to A for all A in set capital A, then C is a lower bound of set A. And set A is said to be bounded below. Set bounded above and below is a bounded set. A set that's not bounded is an unbounded set. So there you go. All right, we need this idea really of upper bounds and lower bounds so we can address least upper bounds and greatest lower bounds. Let A be a subset of an ordered field F which is bounded above. So we've got a set A bounded above. That's the setup. Then B in field F is called a least upper bound or supremum, LUB, of set A if two things happen. B is an upper bound of set A, so every element of set A is less than or equal to element B. And if C is an upper bound of set A, then B is less than or equal to C. All right, so this first one simply means B is greater than or equal to everything in set A. This second one says if we find another upper bound of that set, then that other upper bound, it ain't less than bound B. There is no upper bound of set A less than B. That's because B is the least upper bound of set A. For example, If set A was the set of real numbers consisting of the open interval from 0 to 1, then 1's an upper bound, 2's an upper bound as well, but 1 is the least upper bound. Open interval from 0 to 1, 0 would be a lower bound. In fact, 0 would be the greatest lower bound, and that's the next thing that's defined. Let A be a subset of an ordered field F, which is bounded below. B in the field is a greatest lower bound if B is a lower bound, so everything in the set is greater than or equal to B, and there is no lesser lower bound because, let's see, did I say that correctly? If C is a lower bound, then C is less than or equal to B, excuse me. There is no lower bound greater than B. I said it wrong. There is no lower bound greater than B. B is the greatest lower bound, also called infimum. So the words really describe what we're dealing with in terms of least upper bounds and greatest lower bounds. One more definition, which will turn into an axiom, and then we can define the real numbers. Let F be an ordered field. F is said to be complete if for any non-empty set A of field elements that is bounded above, there is a least upper bound of A in F. So every set that has an upper bound has a least upper bound. Every set that has a lower bound has a greatest lower bound. That's usually one of the first things you prove after a statement that the real numbers are complete. Not only do sets with upper bounds have least upper bounds, one can prove sets with lower bounds have greatest lower bounds. It's a simple little, it follows easily from the axiom of completeness for the real numbers. The rational numbers, they ain't complete. Here's one. Take the rationals, P over Q. P and Q are integers, Q is not zero. They're not complete because if you'll take, in the setting of the rationals, so the field we're talking about is the rationals. In the following example, the only thing that exists is rational numbers. If we'll consider the set A of all rational numbers such that when we square them, we get something less than 2, this has an upper bound. 2 is an upper bound. So is 5. It's got a bunch of upper bounds, but it doesn't have a least upper bound in the rationals. There is no least upper bound for this set. In the reals there is. I could use the square root of 2, but the square root of 2 doesn't exist in this field. So here's a situation where we have a set with an upper bound, but not a least upper bound. All right, well that can't happen in a complete field, so I guess the rationals are not a complete field. All right, you know what makes it work. I've chosen a set here, and as a set of real numbers, its least upper bound is the square root of 2. But in the rationals, there is no square root of 2. Yeah, that's because the rationals have a hole in them at the square root of 2. Completeness is an idea of a continuum. We don't have a continuum in the rational numbers, because there's like a hole in the rational numbers, a gap at the square root of 2. The square root of 2 is not there in the rationals. Neither is the square root of 3, neither is pi. And so I could do a variety of different things and come up with sets with upper bounds of rational numbers that do not have least upper bounds in the field of rational numbers. All right, so definition, we're maybe completing the definition of the real numbers. So the real numbers are complete. Axiom 9, the real numbers are complete. So the real numbers are a complete ordered field. That's my definition 0.9. So field, that's the algebraic properties of the real numbers. Ordered, that's the greater than, less than properties of the real numbers. Complete, that's the continuum part. And probably no surprise, this completeness idea historically is the last one to come into the mathematical realm. An idea of an ordering and of a field is, I want to say, much older. Yeah, it took the mathematical world a little while to come to the realization that negative numbers should count as actual numbers. They came out of the theory of equations. In fact, so did complex numbers, and about at the same time, sometime in the 1500s. These ideas of negative numbers as actually numbers caught on. But historically, certainly the completeness comes last, not to wear out too much of the history stuff, but the idea of completeness dates from Dedekind in the 1850s, maybe the 1860s. So this idea of completeness as a rigorous mathematical concept, it's only 170 odd years old. So not that old. Cauchy used an idea of completeness without explicitly stating it. I think we'll bump into some of those ideas in this graduate class. So there's 9 axioms that define the real numbers, 7 field axioms, an order axiom, and a completeness axiom. So the real numbers are a complete ordered field. Are there other complete ordered fields? Here we go. There's not. Turns out the real numbers are the complete ordered field. In other words, all complete ordered fields are isomorphic. All complete ordered fields are isomorphic. I leave it to you to dig through the details on that from Which Numbers Are Real, an MAA publication from a few years back. The proof of this, it's really tedious. You know what it means to show 2 fields are isomorphic, and you do that in algebra, field isomorphisms. Yeah, you got to take into consideration the ordering and show that the field isomorphism preserves the ordering. So then we would have an idea of a isomorphism between ordered fields. And then you got to deal with the completeness. And somewhere in there, you got to deal with what a real number is. And what you would define it to be is a equivalence class of Cauchy sequences of rational numbers. It's quite involved to go through and establish this. It's nothing new, but to establish that there's only one complete ordered field is a fairly tedious thing. I keep threatening to post notes on that, but I just haven't had the time to hack my way through it and put together something clean. But there's a reference for you for completeness. Okay, we could use the axiom of completeness to define exponentiation of positive real numbers with irrational exponents. In calculus, exponentiation is defined by first defining the log function. You use here we go, the theory of integration to define the natural log function. And then you can go through and define the exponential function based on that. And from that exponential function, you can define what it means to exponentiate positive real numbers to irrational powers. That's the way it's done in a calculus sequence. Ross's book does it in a similar way. An alternative way that the Kirkwood book uses is going directly to the axiom of completeness. So here's what it means. It's a little application of least upper bounds. Here's, we'll take x to be a positive real number and r a positive irrational number. Then x to the r is the least upper bound of the set x to the p, where p is rational and p is between 0 and r. So we're taking this real number and raising it to rational powers that are positive and strictly less than irrational exponent r. In some sense, you're taking a limit. This least upper bound thing, in some sense, it's a limit. If I were to informally approach raising numbers to irrational powers, I'd probably do it in some limit explanation. Take a look at my Calculus 1 notes, and that's a common way to approach it. Here, well, it's sort of like a limit. We've buried it in this least upper bound thing. Do you know this least upper bound exists? Sure, if I can find an upper bound. If I know this set has an upper bound, then I know this set has a least upper bound because it's a set of real numbers and the real numbers are complete. Give me an upper bound of this. Let's see, R is an irrational number. Well, find yourself an integer that's bigger than R. They're out there. And consider x to that integer power. That'll be an upper bound to this. So we do have an upper bound, and the least upper bound does exist. This guarantees the existence of x to an irrational power, and it involves a use of least upper bounds, and so a use of the axiom of completeness. This was for what, x greater than 1. If x is between 0 and 1, then we do a little reciprocal of a reciprocal trick. If we have negative irrational exponents, then we do a little deal with reciprocals there as well. I'll leave the details for you to ponder on that. It's just taking advantage of what we've already defined to extend it to more general settings. All right, we're going to define the measure of a set and certain Lebesgue integrals. Your experience before this class is presumably exclusively with Riemann integrals. Lebesgue integrals will define in terms of suprema and infima of certain things. So we need the following properties. I have labeled this the epsilon property of sup and inf. Least upper bounds and greatest lower bounds. Comes out of Kirkwood's book, as mentioned. It's in Royden's book. I guess I didn't quite find this in Ross's book. This is important because we need this stuff when we take our definitions and we establish things using epsilons and deltas. Well, epsilons in this case for the integrals. Finite alpha is a least upper bound of set A, a set of real numbers, if and only if the following hold. So we're given necessary and sufficient conditions for alpha to be a least upper bound of set A. Part 1, alpha is an upper bound of set A. Yeah, of course, that's necessary. And it needs to be the least upper bound. So we're taking the least in least upper bound and trying to rewrite it in terms of epsilon. For all epsilon greater than 0, there exists a number, x based on epsilon, in set A, such that x based on epsilon is greater than alpha minus epsilon. Yeah, alpha is a least upper bound. So if you go any less than alpha, which alpha minus epsilon is, that's less than alpha, then you're going to pick up elements of the set. So here's a way to classify a least upper bound using epsilons. How about a greatest lower bound? Yeah, same thing. Beta is a greatest lower bound of set A, a set of real numbers, if beta is a lower bound, and let's see, greatest lower bound. Well, what if we looked at something a little bit greater than beta? Well, let epsilon be greater than 0, and let's consider beta plus epsilon. That's a little bit greater. That won't be a lower bound anymore, so there must be something in the set that's less than beta plus epsilon. Beta plus epsilon is no longer a lower bound of the set. Beta plus epsilon is not. So it's simply an idea of taking the least and expressing it in terms of some epsilon stuff, and taking the greatest and expressing it in terms of some epsilon stuff. This is one of the most important things when we get to defining the Lebesgue integration from your past that we'll use pretty often. And I'll refer back to it when we do. Sequences of real numbers. Hey, you're familiar with the idea of a sequence of real numbers and epsilon definitions about limits of sequences. Epsilon, it's really epsilon n definition of a limit of a sequence from Calculus 2. Subject you to rehashing these definitions in the comprehensive exams. Something not from calculus, you might find it buried in the calculus book somewhere as a chapter challenge exercise or something, is the idea of a Cauchy sequence. Cauchy sequences, very, very important in what we're going to do. Very, very important in analysis. A sequence of real numbers, A sub n, so we're using this notation to represent sequences, by the way, set brackets and subscripted letters. So that's the sequence, A1, A2, A3, and so forth. That's a common notation. You got a problem with it? Yeah, a little bit, because set brackets I mean, a sequence is not just a set. A set doesn't repeat elements, and a sequence can. In a set, the elements don't come in any particular order. And in a sequence, the most important property of the sequence is the order. So maybe set brackets aren't the best notation. They're a common notation. That's what I'm going to use. Royden, I think, uses set brackets. So a sequence of real numbers is a Cauchy sequence if, for all epsilon greater than 0, there exists a capital N based on epsilon, such that if n and m are greater than capital N, then the absolute value of a sub n minus m is less than epsilon. Oh yeah, we measure distance in the reals with absolute value. So this says, you give me an epsilon greater than 0, I can find a capital N such that beyond, for values of the index, beyond that capital N, the distance from a sub n to a sub m is always less than epsilon. So out there, when the indices get real big, these terms get close to each other. It's easy to show that a convergent sequence is Cauchy. All you need is a triangle inequality. Here's a triangle inequality in the setting of real numbers. But the converse of that's quite challenging. The fact that a Cauchy sequence of real numbers is convergent, so here's a theorem for you. A Cauchy sequence of real numbers is convergent, but that's complicated. It requires the axiom of completeness. So the proof of that claim is a little bit more substantial. See my analysis notes, and all the stuff is in the analysis notes. But the fact that that convergent sequences are Cauchy, easy, and Cauchy sequences of real numbers are convergent, not easy but true, tells us a sequence of real numbers is convergent if and only if it's Cauchy. So in the setting of the real numbers, Cauchy and convergent are equivalent. You may encounter some other settings where you appeal to the behavior of Cauchy sequences in order to get completeness. In the complex numbers are a continuum, the complex numbers are complete, but we set all this stuff up in completeness here in terms of upper bounds and least upper bounds, which means we use the ordering. Remember, the complex numbers, they ain't got an ordering. There isn't a greater than, less than on the complex numbers. So if we're going to talk completeness, it can't be done the way we did it here. It can't be done in terms of least upper bounds and greatest lower bounds. There isn't a greater and a lesser in the complex setting. It's got to be done some other way. It turns out it's done this way. It's done using Cauchy sequences. In metric spaces, a metric space is complete if Cauchy sequences converge. And in a metric space, you can measure distance, and that's exactly what we're doing here. The idea of a Cauchy sequence makes sense in a metric space. Completeness is defined in terms of Cauchy sequences. So anyhow, Cauchy sequences are a big deal. Let's talk subsequences. So we'll take a sequence, a sub n, and we want to get a subsequence of that sequence. This comes up in some of our graduate stuff. Let n1 less than n2, and so forth, be a strictly increasing sequence of positive integers, natural numbers if you like. Then a sub n1, a sub n2, blah, 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 is a subsequence of a sub n, and it's denoted this sequence a sub n sub k, or the subsequence a sub n sub k. So the fact that we've taken these natural numbers in order implies when you pull off these terms from the original sequence, you're maintaining the same order. A sub n sub 2 appears to the left of a sub n sub k in the subsequence, just like they did in the original sequence. So subsequences. A number L is called a subsequential limit of sequence a sub n. All right, so we're looking at the original sequence a sub n and talking about a subsequential limit L of that original sequence if there is a subsequence of a sub n that converges to L. All right, so the sequence a sub n itself may not converge, but it might have convergent subsequences. If it's got one that converges to L, then L is a subsequential limit of a sub n. And all this is being done in a conversation about sequences. And we might talk or relate this to limit points of sets as well. And I haven't got all the topology from senior level analysis in these notes. But we might talk limit points of a set and tie that in somehow or other with these sequence ideas as well. Definition of two special kinds of subsequential limits. Let A sub n be a sequence of real numbers, then lim_sup of A sub n, lim_sup is how this is read with the overline, is the least upper bound of the set of subsequential limits of A sub n, and liminf of A sub n is the greatest lower bound of the set of subsequential limits of A sub n. All right, so we're looking at the set of all subsequential limits. We just defined what a subsequential limit is, so take the set of all of those. Lim_sup is the least upper bound of these. Liminf is the greatest lower bound of these. Well, provided these are bounded. Otherwise, I might run across some infinities and negative infinities and some of this stuff. Our most common application will be to bounded sequences. An alternative definition, this is mentioned in Royden, so it may pop up in the book. I'm going to make some additional comments about this, but we can also write lim_sups as a limit of the sup of the tail, a set consisting of the tail of the elements of the sequence, or an inf of the tail of the elements of the sequence. This is an alternative way. Hey, I got a better way than all this stuff to talk about lim_sups and liminfs. For a given sequence, A sub n, we get the property that lim_sup A sub n and liminf of A sub n are themselves subsequential limits. It's one of the reasons I like Kirkwood. He does a thorough job with his stuff in his analysis book. So we can say that lim_sup is the greatest subsequential limit. How convenient. Lim_sup is the greatest subsequential limit of that sequence, and liminf is the least subsequential limit. Little disclaimers when we get the negative infinity stuff out, least and greater. Maybe I should modify how I use those words. If we happen to get infinity out as a subsequential limit, infinity is not a number, but it can be a limit. So this streamlines all this conversation up here, at least for bounded sequences. So lim_sup is the greatest subsequential limit, liminf is the least subsequential limit. How convenient. But that follows, that's proven from the definitions above. And it makes conversations about lim_sups and liminfs of sequences a little less bulky, a little less cumbersome. Some properties of lim_sups and liminfs. The lim_sup of a sum, A sub n plus B sub n, is less than or equal to the sum of the lim_sups, and the sum of the liminfs is less than or equal to the liminf of the sum. A standard proof concerning lim_sups and liminfs from senior level analysis. Kirkwood does this, Ross does this. I guess it's not even in the Royden book. But standard behavior in terms of lim_sups and liminfs, something we may need along the way. We'll quote theorem 0.4 if we do. Let's talk topology of sets, open and closed sets and compact sets and connected sets, topological ideas. All right, I warned you, just a blast of information. Set U of real numbers is said to be open if for all x an element of U, there's a delta based on that x element greater than 0, such that the open interval x minus delta to x plus delta is a subset of that set U of real numbers. So open means, you may have a variety of verbiage in your background, set's open if every element of the set is an interior point. And interior points are basically defined like this. I always teach it in senior level analysis, is the important thing is you got wiggle room in an open set. You go to any point in that set, let's call it X, you can wiggle to the left and the right a little bit from X and stay inside the set. Why would you want to do that? Why are open sets so important in analysis? Because we're going to want to take limits, and you're going to want to let X vary a little bit to the left and the right. You got open sets, you're good to go. That's why open sets are important in analysis. A set's said to be closed if its complement is open. Okay, that's Kirkwood and Ross's definition. It's a super common definition of closed. You may have seen some other places where closed is defined slightly differently, maybe in terms of containing boundary points. Our complex variables class says some things like that. This approach here is cleaner, actually. But open sets, you got wiggle room around open sets. What do you know about closed sets? Their complements are open, which doesn't tell me anything directly about closed sets itself. So I could maybe use a little bit more equipment if I want to describe closed sets. Okay. Next, consider a bunch of open sets. Let's see, this is a theorem, Kirkwood and Ross. Take U1, U2 up to U sub n to be a finite collection of open sets. The claim is the intersection of that finite collection of open sets is open. I guess Royden excluded this because it's really fundamental. So it's understood to be background. Yeah, finite intersection of open sets is open. Here we're thinking open sets of real numbers, but this is true in lots and lots of settings. It's true in the most general setting I can think of, which is a topological space. It's actually by definition is true in a topological space. Finite intersections of open sets are open. Part B, if I take any collection of open sets, the union of those open sets is open. Unions of arbitrary collections of open sets are open. How many open sets do we have here? I don't know. Could be anything. Could be finite collection. Had to be a finite collection in part A when we did the intersection. For the union, could be finite, could be infinite, could be countable, could be uncountable. More on cardinality later. Any collection, an arbitrary collection of open sets has a union which is open. Standard proofs given based on the above definitions in senior level analysis. The closed sets satisfy the following. The empty set is closed. The real numbers themselves form a closed set. Actually, both of these are open sets as well. If we take any collection of closed sets, then the intersection is closed. If we take a finite collection of closed sets, then the union is closed. It's the same thing we had upstairs? It isn't. Up here we had, for open sets, finite collection of open sets, intersection is open. Down here we had finite collection of closed sets, union is closed. So the role of the union and the intersection were interchanged when we went from open sets to closed sets. Any idea why that might be? How are open sets and closed sets related? What was a closed set? A set whose complement is open. So if I want to use information about open sets and prove stuff about closed sets, I guess I'd use complements. Do you know how the complement procedure affects an intersection of sets? Yeah, it turns it into a union of complements. The complement of the intersection is the union of the complements. Sound familiar? It's the first thing we said in here. It's De Morgan's laws. So De Morgan's laws can be used to prove B and C down here from A and B up here, for example. Standard senior level analysis argument. All right, let's see. We just saw a countable infinite intersection of open sets may not be open. A finite collection of open sets may be open. Countable infinite union of closed sets may not be, should read, may not be closed. A little typo there. So what this didn't say is what happens when I have a maybe a countable collection of closed sets and I union them, or when I have a countably infinite collection of open sets and I intersect them. Where we had finite, what happens if I try to replace this with infinite? Well, it doesn't work. The result doesn't hold, as we can show, and you show in senior level analysis by example. Well, what kind of set do you get when you take a countable intersection of open sets or a countable union of closed sets? Well, we're going to give those a special name, and they'll be called G delta sets and S sigma sets. So the kinds of sets you study in senior level analysis is a little oversimplified, but basically it's open and closed sets. The kind of sets we'll study in graduate real analysis will include open and closed sets, and it'll include G delta and S sigma sets and some other classes of sets. We'll see this early on in our classification of sets. I'm impressed if you did G delta and S sigma sets in your senior level analysis. I don't have time for that in senior level analysis because of other obligations. But we'll define these classes of sets motivated by the behavior of unions and intersections of open and closed sets. Okay, I declare the following as the most important result from analysis 1 with an eye towards graduate real analysis 1. It tells you what an open set of real numbers looks like. That is, it classifies open sets of real numbers. Got it? This is a big deal. We're going to do, in graduate real analysis, we're going to do measure theory, and we're going to do Lebesgue integration, Lebesgue measure and Lebesgue integration. And the measure stuff is so motivated by this next result. From senior level analysis, you know, Kirkwood and Ross do both of these, that a set of real numbers is open if and only if it is a countable union of disjoint open intervals. Countable union of disjoint open intervals. If we were in class, I'd have you mouth those words along with me. This is so essential. A set of real numbers is open if and only if it's a countable disjoint union of open intervals. So the three magic words are countable, union, disjoint open. I'm going to clump those last two together. Disjoint union, maybe. And we'll introduce some symbols to indicate what a disjoint union is to distinguish it from non-disjoint unions. But anyhow, countable disjoint union of open intervals. So open intervals are examples of open sets, and unions of open intervals are examples of open sets. The word countable snuck in. You know, we didn't have that restriction upstairs. When we took unions of open sets, we allowed arbitrary unions. Yeah, any collection. It didn't have to be countable up here. Well, then we know something a little more restrictive when we're talking open sets of real numbers, right? This offer only valid for the real numbers. There may be some more abstract spaces out there, topological spaces where open makes sense, open and closed makes sense, but maybe this type of result doesn't hold. But for the real numbers, and that's our concern, is sets of real numbers. I can classify what an open set of real numbers looks like. And we're going to use open sets a bunch in the measure theory stuff. A largely self-contained proof of theorem 0.7 is in my online notes for analysis 1. So I've got a proof of that set up with pretty much all of the background stuck in there. Get it in your head at the very least. Set of real numbers is open if and only if. Countable disjoint union of open intervals, which tells you, gee, there's something really fundamental about open intervals when it comes to a conversation about open sets of real numbers. And you're in an analysis class, and analysis is all about open sets. So there's something super fundamental about open intervals. Not every open set is an open interval, but open intervals make up open sets of real numbers in this sense right here. Just hate to leave it behind us. Theorem 0.7. Okay, let's shift gears to a slightly different topic, but also a topological topic. Let A be a subset of the reals, so a set of real numbers. The collection of sets, I sub alpha, is said to cover A if A is a subset of the union of the I sub alphas over index alpha. And it's common to introduce a collection given an index. How many of these I sub alphas are there? I don't know. There's one for every alpha, however many alphas there are. cardinality of the indexing set. I dealt with it in the past, but anyhow, union up those I sub alphas. If that's a superset of set A, then this is said to be a cover of set A. If each of the I sub alphas are open, then it's called an open cover of A. And we're interested in open sets, and so we're interested in open covers. If the cardinality of this collection of sets is finite, it's called a finite cover. So how many are there? Well, could be anything. If there's a finite number of them, then it's called a finite cover. And we're interested in, some of these words are to start to sound familiar, a finite open cover of set A we're interested in. A set of real numbers is compact if, by definition, every open cover of the set has a finite subcover. So I'm interested in covering sets of real numbers with open sets and whether or not they have finite subcovers. So for a compact set, I can cover it with an arbitrary collection of open sets. And I can throw out all but a finite number of them and still have an open cover. That's a property of compact sets because that's the definition of compact sets. That's what a compact set is of real numbers. That's what a compact set is in a topological space. So this is the definition of compact. You may have something else in your head. We're about to talk about it, but this is what a compact set is. Why are compact sets important? Well, it kind of lets you make a transition from the infinite to the finite when you have a compact set. If I have a continuous function defined on some set, does it have a max and a min? I don't know. If I have a continuous function defined on a compact set, all this happening in the setting of reals, it'll have a maximum and a minimum. Your favorite kind of compact sets from calculus are closed and bounded intervals, A to B. The extreme value theorem deals with continuous functions on closed and bounded intervals, A, B, which are examples of compact sets. Yeah, compact sets let you make a transition from the infinite to the finite in some sense. Now that's just me talking, that's informal, but that's the reason compact sets are important. Can you tell me what a compact set of real numbers looks like? Sure, Heine-Borel tells us that. This is in Kirkwood, it's in Ross, I suspect it's even in the Royden book somewhere, certainly referenced many times. A set of real numbers is compact if and only if it's closed and bounded. Okay, then why did we get into all of this stuff about open covers and finite subcovers if all a compact set is closed and bounded? Because it's not all a compact set is closed and bounded. There are compact sets that are not closed and bounded. Sorry, I should say there are closed and bounded sets that are not compact. These aren't the same thing elsewhere. Now in the real numbers, yeah, Heine-Borel holds in the real numbers. And compact and closed and bounded are the same ideas for sets of real numbers. Actually, if we were to deal with Rn, the vector space you deal with in sophomore linear algebra, you got a way to measure distance in there. The norm of a vector lets you measure distance, put a metric on that space. In Rn, a compact set is closed and bounded, and conversely, compact if and only if closed and bounded in Rn. But there's other spaces out there, and they're infinite dimensional spaces. In an infinite dimensional space, I can give you an example of a closed and bounded set, which is not compact. That is a closed and bounded set that doesn't satisfy this open cover, finite subcover stuff. It's not compact. Now, that's a fairly exotic result, but your graduate students will pry out of your head the following idea. All compact sets are closed and bounded, and all closed and bounded sets are compact. It's false. It doesn't take much to fix it, though. A set of real numbers is compact if and only if it's closed and bounded. There's more to life than just the sets of real numbers. And I do have to go to an exotic place to find a closed and bounded set that isn't compact, but we'll do it. That's the kind of thing we'd likely cover in real analysis too, when we do LP spaces or possibly Banach spaces and Hilbert spaces. I can find examples of closed and bounded sets that are not compact. It's actually not that hard once you make sense out of those spaces. But a set of real numbers is compact if and only if it's closed and bounded. Real analysis 1, largely a study of sets of real numbers. So Heine-Borel will apply in real analysis 1. It applies anytime you're dealing with sets of real numbers. But if you're dealing with sets of other things, maybe it doesn't apply. Just be careful. A compact set is not just one that's closed and bounded. A compact set is, by definition, one in which every open cover has a finite subcover, and that's the important property of them. What the Heine-Borel theorem tells you is, no, in a setting of real numbers, it's easy to recognize compact sets, because in the real numbers, they're just closed and bounded. So this is a useful result for recognizing important compact sets in the setting of real numbers. And they're important because every open cover has a finite subcover. That's what's important about compact sets. Let's move on to an idea about connected, also a topological idea. And you might even see these ideas in connection with connected graphs, an idea of a separation. A separation of a set A is two open sets U and V such that U intersect V is empty, so they're disjoint open sets. U intersect A is non-empty and V intersect A is non-empty. So both U and V touch set A. And if you'll take U intersect A and union it with V intersect A, you'll get all of set A. So set A is a subset of these two open disjoint sets. Such a thing is called a separation of set A. If a set A doesn't have a separation, then it's called a connected set. So well, it's kind of a sideways way of defining connected. We defined what a separation is and then said a set's connected if it doesn't have a separation. You do that kind of thing when you do linearly independent. You define what a dependence relation is on a set of vectors, and then you say, well, this set's linearly independent if it doesn't have a dependence relation. So the logic's kind of similar to that. It's defined in terms of these disjoint open sets. This little symbol snuck in, as I mentioned a while ago. When you take a union symbol and put a little dot in it like that, it means disjoint union. Are you sure these are disjoint? Yeah, U and V were disjoint. This is a subset of U and this is a subset of V, so these are disjoint. But we'll be quite interested in when we have just regular unions and when we have disjoint unions. Unfortunately, the Riemann book doesn't use this symbol. It's not a standard LaTeX symbol. It's commonly used. Google disjoint union and see if this doesn't pop up. But the idea that we have disjoint unions is going to play a big role in what we do. So we'll be using that symbol a fair amount in part one. So separations and connected sets. By the way, this holds in any topological space. Anywhere I can talk about open sets, we could talk about this kind of stuff. Our implication, or well, our program is to apply this stuff to the sets of real numbers. You know what a connected set of real numbers looks like? No surprise, it's an interval. Ooh, or a singleton, a single point. Yeah, that's connected. But single points don't count as an interval. What was an interval? Had at least two things in it, and when any two things was in it, all the stuff between those two things was in it in a conversation of ordered fields. So the connected sets are intervals and single points. These don't count as intervals. That's why it has to be tacked on as an extra class. And no surprise there, of course, the connected sets are intervals, well, or singletons. Let's talk a little bit about cardinalities. It's come up already. Cardinalities play a role in analysis. And we're going to lightly touch on these ideas. This really belongs in the realm of set theory. Maybe you did some of this in math reasoning. More likely you did some of this in senior level analysis. Two sets A and B are said to have the same cardinality if there's a one-to-one and on-to function from set A to set B. So a study of cardinality is really a study of one-to-one and onto functions. Same cardinality means there's a one-to-one and onto function from set A to set B. This might be called a one-to-one correspondence. I can put the elements of A in a one-to-one correspondence with the elements of B. That is, by definition, saying those sets are the same size. Well, cardinality is a better word. Size becomes ambiguous when I start looking at infinite sets. But same cardinality, one-to-one and onto function from one to the other. The elements can be put in a one-to-one correspondence with each other. A set S is said to be finite with cardinality n if there's a one-to-one and onto function from S to the set 1 through n, where n is some natural number. So then I can say the number of elements in set S is n. The empty set is said to have cardinality 0. It's finite with cardinality 0. Sets that don't have finite cardinality are infinite sets, and that's where stuff gets really interesting. A set is said to be countable if it has the same cardinality as the natural numbers. Sets that are not countable are called uncountable. All right, so you get the funny result that some infinite sets are bigger than others. So there's levels of infinity, standard property of infinite sets from senior level analysis. So we're interested in countable sets and we're interested in uncountable sets. It turns out there's various cardinalities of uncountable sets as well. Some results about cardinality. The union of a countable collection of countable sets is countable. So in a sense, you start with everything countable, you're stuck with countable. You got a countable collection of countable sets. That's a bunch of sets. And each set's big, infinite, potentially. Countable collection, still countable. Countable union of countable sets is countable. I guess a bigger surprise is the real numbers in the interval 0 to 1 form an uncountable set. So there's more numbers between 0 and 1 than there are natural numbers, and there's an infinite number of both of them? That's right. So here's two infinite sets, say the natural numbers and the real numbers between 0 and 1. They're both infinite, but in a sense, there's more of these. There's more numbers between 0 and 1 than there are natural numbers, yet there's an infinite number of both. Yeah, there's big infinities and there's little infinities. The argument to prove this is the standard Cantor diagonalization argument from senior level analysis. We'll be talking cardinalities a fair amount in graduate real analysis 1. We can use a tangent function, which is a one-to-one and onto mapping from 0, 1 to all of the reals properly adjusted. So it follows that the cardinality of the interval 0, 1 is the same as the cardinality of the reals. So what it amounts to when studying real numbers is it seems like there's only two levels of infinity. There's countably infinite and this uncountable infinity. Well, it's a little more involved than that. We're going to associate cardinal numbers with sets. Excuse me. As follows. We'll say that two sets share the same cardinal number if they have the same cardinality. That is, if there's a one-to-one and onto function from one set to the other. The cardinality of set X is denoted with usual stuff. It looks like absolute values, but usual symbols. It means the cardinality of set X. And we're going to order the cardinal numbers. We're ordering the cardinal numbers as follows. So we're going to talk about a greater than and less than, greater than or equal to, less than or equal to, in terms of cardinalities of sets. And it's all going to be described in terms of one-to-one and onto functions. Part 1. If X and Y are sets, and there's a one-to-one function from X into Y, not necessarily onto, then the cardinal number of X is no larger than the cardinal number of Y, denoted cardinality of X is less than or equal to the cardinality of Y, or cardinality of Y is greater than or equal to the cardinality of X. So What it really means is I can put all of the elements of X in a one-to-one and onto, or one-to-one correspondence with some of the elements of Y. It's into Y, not necessarily onto. So the idea is, yeah, Y contains at least as many elements as X does, as many as, it's precisely it is what it says right there, the stuff about one-to-one functions. If this first part holds, but there is not an onto function, we left it up in the air up here. We didn't say there was or wasn't. That's why we got the or equals to. If there is no onto function from X to Y, then the cardinality of Y is strictly larger than the cardinal number of X. Cardinality of X is strictly less than the cardinality of Y, or similarly. We want to probably informally interpret this in terms of Y has more elements than X. And that's what we're saying here between you and me. What it means is all this stuff about one-to-one functions and onto functions, yes or no. That's the formal definition of cardinality, but you're still thinking sizes as sets. It's just it's going to be weird when you have these infinite sets. Cantor's theorem in the Kirkwood book, I guess maybe it's not in the Ross book, says the following. This is just a surprising result about cardinalities. It says the cardinal number of the power set of X. Remember, the power set was a set of all subsets of set X. Let me denote it with a calligraphy P, the power set of X. Claim is the cardinality of the power set is strictly larger than the cardinal number of X. That is, the cardinality of X is strictly less than the cardinality of the power set of X. Okay, so this means you could make bigger and bigger infinities, bigger and bigger cardinal numbers, maybe. Take the real numbers. Take the power set of the real numbers. That'd be an infinity bigger than the cardinality of the reals. Take the power set of the real numbers. That'd give you yet another level of infinity, a bigger infinity. And keep taking power sets, you keep building bigger and bigger infinities. So there's a lot of big infinities out there. This is some of the weird stuff you see in behaviors of infinite sets. This stuff is really baby set theory. And maybe not so babyish, but this idea of cardinal numbers falls in the realm of set theory. There's readable senior level books on set theory out there. Sadly, ETSU doesn't have a set theory class. For a finite set, say cardinality of set A is n, it's a natural number. It's easy to show the cardinality of the power set is 2 to the n. Induction, you can use induction to show that. You can use counting arguments to show that. I think you can even use the binomial theorem to show that. Based on this fact, it's a notation. It's common notation to say the cardinality of the power set of A is 2 to the cardinality of A. Don't read too much into it, it's just a notation. But it's a notation motivated by the behavior of sets of finite cardinality. It can be shown that, okay, some properties of cardinal numbers, the cardinality of the natural numbers, that's the smallest infinite cardinal number. If you have an infinite set, it's at least this big. And that can be proved. This cardinality is denoted aleph naught. So here comes the aleph. Aleph naught is the cardinality of the natural numbers, sub-0, because it's the smallest infinite cardinal number. So the cardinality of any countable set then, countable meaning cardinality is the same as the natural numbers, the cardinality of any countable set is this aleph naught. By Cantor's theorem, this thing upstairs about power sets, this little property here would say aleph naught is the cardinality of the natural numbers is strictly less than the power set of the natural numbers. That's what Cantor's theorem says. You take any set, its cardinality is strictly less than the cardinality of its power set. That set we're using here is the natural numbers. So we get the inequality there. And this we would, using the notation here, we would denote this as 2 to the aleph naught, because it's should be denoted 2 to the cardinality of the set of which we're taking the power set. And that's the natural numbers, and the natural numbers have cardinality denoted aleph naught. So it's really just symbols for the most part. Okay. Now for something a little interesting and bordering on math philosophy. The real numbers are sometimes called a continuum. And the cardinality of the real numbers is called the cardinality of the continuum. It's sometimes denoted with a C for continuum, the cardinality of the continuum. It can be shown, and here's your reference, speaking of a readable sort of junior, senior level set theory book. It's this one by Herbacek and Yek. The ETSU library has a copy. It's got some pencil marks in it. I put in it years ago. But excellent introduction to set theory book, reputable introduction to set theory. There's something called naive set theory where you play around with unions and intersections. This is more the good detailed stuff with the cardinalities and so forth. But it can be shown that the cardinality of the real numbers, the cardinality of the continuum, is the same as the cardinality of the power set of the natural numbers. That is 2 to the aleph naught. So we know aleph naught is less than the cardinality of the continuum. We know the cardinality of the continuum is the same as 2 to the aleph naught. Is there something in between? I say it's natural to ask if there's a cardinal number, beta, that's bigger than aleph naught and less than the cardinality of the continuum. These represent cardinalities of sets. Aleph naught is the cardinality of the natural numbers. C is the cardinality of the real numbers. So, is there some set, a superset of the natural numbers and a subset of the reals, that has a cardinality that's strictly greater than the cardinality of the natural numbers and strictly less than the cardinality of the real numbers? Unfortunately, under the standard axioms of set theory, this is an example of an undecidable. This is neither true nor false under the standard ZFC axioms of set theory. It's Zermelo, Frankel, a couple of folks. The C stands for choice, the axiom of choice. We'll encounter the axiom of choice in some of the stuff we do, pops up in analysis. But the idea with these infinite cardinal numbers is, well, this one is less than that one. Is there one in between? There's a subset of the real numbers that's greater in cardinality than aleph naught and less in cardinality than the cardinality of the continuum. This is called a continuum problem because it deals with the cardinality of the continuum, the cardinality of the real numbers. In 1900, David Hilbert, there's his years, big name analysis guy in the first half of the 20th century. 1900, to open the new century, David Hilbert gives a list of 23 unsolved problems at the famous International Congress of Mathematics in Paris. And the first problem on his list is a continuum problem. The continuum hypothesis states that there is no such set B as described above. So the continuum problem is there such a set or not? The continuum hypothesis is that there's not such a set. Well, can you prove the continuum hypothesis? Funny story. In 1939, Kurt Gödel, of Gödel's incompleteness fame, proved the continuum hypothesis is consistent with the ZFC axioms of set theory. Here's a little reference on that. So what Gödel shows in 1939 is you can't disprove the continuum hypothesis. Well, it gets worse. In 1963, Paul Cohen proved the continuum hypothesis is independent of the ZFC axioms. There's your reference on that. What that means is he can't prove it either. So it's neither provable nor is it disprovable. It's undecidable under the axiom, the ZFC axioms of set theory. So here's an example of a really wild claim. It's neither true nor false. which means you could take it and add it to the ZFC axioms of set theory as an additional axiom, the continuum hypothesis, or you could take its negative, its negation, and add that as another axiom. I'll leave it to you. It's pretty interesting stuff to read more about Kurt Gödel and this idea of undecidability. There's a number of popular level books out there that are readable. They don't have to get into the weeds and all the details of the set theory. I like math a lot, but man, some of that set theory stuff is pretty tedious stuff by my standards, and I can put up with a lot of tedious stuff. But there's some popular level books out there on Gödel's proofs. Paul Cohen was awarded the Fields Medal in 1966 for his proof. And this is why the continuum hypothesis is said to be undecidable within the ZFC set theory axioms. Under the hypothesis, under the assumption of the continuum hypothesis, we'd say aleph 1 equals 2 to the aleph naught equals c. This is the continuum hypothesis boiled down to the little symbols we've introduced. It's the first time we've used aleph 1. Well, we'd use aleph 1 because under the continuum hypothesis, that's the next level of infinity after aleph naught. Under the continuum hypothesis. So if you assume the continuum hypothesis, you'd call the cardinality of the continuum aleph 1. Under the assumption of the continuum hypothesis, we get the following. I bring this up because this is a big deal in what we're about to do. Aleph naught is a cardinality of the natural numbers. Aleph 1 is a cardinality of the real numbers because under the continuum hypothesis, it's the next level of infinity. And we get aleph 2 is the cardinality of the power set of the reals. So this would tell you how many subsets of the reals there are. Now I'll mention this because in a sense, in your senior level analysis class, you studied the real numbers and maybe subsets of the real numbers, and countable versus uncountable sets. You were sort of stuck studying things at this level. In this class, we're going to be interested in all the subsets of the real numbers. In this class, we're more at these two levels. We've really upped it a level of infinity by studying subsets of the sets of real numbers, and we want them to have certain properties. We want to measure them. We want to do something called a Lebesgue measure. And we want to Lebesgue measure every set of real numbers. It won't work. The desired properties we have cannot be satisfied, as we'll argue, but probably not prove all the details on that. It's set theory. But in this class, really, it's more a class about the power set of the reals. Senior level analysis was really a class about the reals, and this is a class about the power set of the reals. Congratulations, you've gone up a level of infinity. So cardinal numbers will pop up in what we discuss. Not a great deal, but somewhat. Riemann integration, well, you saw Riemann integration developed in calculus, right? Calculus 1. They do a pretty good job of developing Riemann integration. Chapter 6 of the Kirkwood book, chapter 6 of this Ross book, the two books we normally use in senior level analysis, covers the development of the Riemann integration. This stuff is also in Royden's section 4.1. I'm going to relegate all this conversation of Riemann integration to a supplement, the Riemann-Lebesgue theorem, in which we'll go through and give necessary and sufficient conditions for a function to be Riemann integrable. And we'll do this pretty early on. It's like treat this also maybe as background information part 2. You know from your calculus 1 experience that continuous functions are Riemann integrable. But does a function have to be continuous to be Riemann integrable? No, in calculus 2, you integrate over discontinuities. You integrate over vertical asymptotes, for one thing. So what are the necessary and sufficient conditions for a function to be Riemann integrable? It turns out, a little more details in there, that function needs to be not too badly discontinuous. You know you can integrate over discontinuities. Well, how badly discontinuous can a function be and still be Riemann integrable? The answer is the set of discontinuities can have at most measure 0. Let me try to look you in the eyes. You don't know what measure 0 is because you hadn't taken graduate real analysis 1. So we need to define this measure idea, what it means, and the fact that a function is Riemann integrable if and only if its set of discontinuities has measure 0, whatever that means, implies there's a motivation to try to integrate functions that are even more discontinuous than that, and there's lots of them out there. And that's what this class is about. So in the beginning, when we get into the real analysis 1 material, we'll talk about measure and what the measure of a set of real numbers means, and that's when we'll look at the power set of the reals. We'll use that idea of measure to go through and define something called Lebesgue integration. Why you want to do more integration? Because I can only integrate functions that are sufficiently continuous, not too badly discontinuous, as motivated by the Riemann-Lebesgue theorem. So that's the plan. This is the essential background. I'll put together, try to get a video put together on the Riemann-Lebesgue theorem, and we'll go through that fairly quickly. It is background material, but it's very much more motivational material. The stuff in this video, this is the stuff you need to know to get into this class, and will be appealing to the results from this video and these notes. But we also need to look at the Riemann-Lebesgue theorem because that motivates what we're doing. So this was background, on to motivation. Hopefully I'll see you there in a video on the Riemann-Lebesgue theorem shortly. Have a nice day.